Okay, let's dive right into this. Welcome to this explainer where we are going to completely decode record structures for your Cambridge Computer Science exams, and more importantly, reveal exactly what those senior examiners are looking for when they grade your papers. Whether you are tackling syllabuses 0417, 0478, 0983, 0984, 2210, or our main focus today, the 9618 AS and A level, mastering the art of the record structure is absolutely essential. It's a game changer. Think of your exam strategy like a street artist approaching a blank concrete wall. To make a masterpiece, to truly make your mark, you need bold strokes of creativity. But those strokes have to be backed by a rock-solid underlying structure, or the whole thing just falls apart. That's what we are doing today. We are going to transform how you approach these complex data structure questions, shifting you from just panic-dumping raw computer science facts onto the page to demonstrating true, top-tier analytical depth. Let's get to work.
Here is our roadmap for today's explainer. We'll start with the challenge, move into core principles, lay out a procedural framework, discuss the method mark strategy, look at examiner warnings, and finally wrap up with algorithm evaluation.
All right, section 1, the challenge. Let's look at exactly why these specific questions trip up so many candidates right out of the gate.
Why do students struggle so much to apply record structures to completely unfamiliar contexts? You know, this specific issue is the root cause of lost marks across the board, year after year. Let me paint a picture for you based on real Cambridge past papers. In the exam room, we typically see two types of students who struggle here. Let's call our first student Alex. Now, Alex studies hard. Alex overloads their exam answers with every raw computer science fact they can remember. They can recite the textbook definition of a record, they know how to declare one in pseudocode, but when the exam asks them to design a system for a theme park ticketing database, they completely freeze. There is absolutely no analytical depth. They don't link their memorized facts to the specific scenario provided. And then we have our second student. Let's call them Sam. Sam rushes. Sam feels the clock ticking, reads the first half of the question, completely misses the critical command word requirements, like the difference between describe and evaluate, and immediately starts writing a generic, messy answer. Sam's logic is all over the place. Both Alex and Sam fail because they can't bridge the gap between theory and application. They don't adapt to the unfamiliar context. They lack the structural foundation to make their bold strokes count. So, to overcome the struggles of Alex and Sam, we need to completely rethink how we approach the fundamentals.
Moving on to section 2, core principles. Before we look at advanced exam strategy, we absolutely must define our foundational tools. The sheer elegance of this definition is striking when you really think about it. A record structure is a data structure holding different data types under one identifier. Now contrast this with an array. An array is fantastic, right? But it typically only holds items of the exact same data type. You get a list of integers or a list of strings. But let's be real, the real world is incredibly messy. The real world doesn't neatly fit into a single, uniform data type. Think about a massive database for a hospital. A single patient profile has a name, which is a string. They have an age, which is an integer. They might have a critical condition status, which is a Boolean, true or false. A record structure allows us to logically organize this highly complex, varied information by grouping these related but entirely different types of data under a single unified identifier. It's literally bringing order to chaos. When you understand that a record structure is essentially a digital filing cabinet for real-world entities, the way you write your algorithms completely changes.
And this brilliantly illustrates our next point, drawn directly from the academic benchmarks for this Cambridge syllabus. The assessment framework prioritizes analytical depth over superficial breadth. So what does this actually mean for you sitting there sweating in the exam hall? It means simply listing everything you know about record structures, like our friend Alex does, just isn't going to cut it anymore. Examiners don't want a brain dump, they demand logical, structured reasoning. This is where you need to apply what we call the PEEL framework: point, evidence, explanation, link. When you write your answer, you make your point about using a record structure. You provide evidence from the scenario, like quoting the specific data types required. You give your explanation of how the record structure solves the problem efficiently. And finally, you link it back to the overall objective of the question. Superficial breadth might accidentally get you a mark or two, but analytical depth using the PEEL framework, that is exactly what gets you the A-star.
Before we continue, subscribe to our YouTube channel Ace the Exams, at @acetheexams_IGCSE to excel in your Cambridge examinations. Click that subscribe button and hit the bell icon right now. Okay, let's look at the cognitive domains. To achieve that required depth we just talked about, your answers need to simultaneously hit 3 distinct cognitive domains: knowledge and understanding, application, and analysis. Knowledge and understanding is just your baseline. Do you actually know what a record structure is? Application is the very next step. Can you write the pseudocode or program code to implement it in the specific, weird scenario they gave you? But analysis? Analysis is where the real magic happens. This is where you extract meaning from binary representations, perform complex calculations, draw evidence-based conclusions, and justify exactly why a record structure is superior to parallel arrays for this specific problem. It requires intense command word decoding. If the command word is evaluate, you cannot just describe. You have to weigh the pros and cons. Your answers need to hit all three of these domains simultaneously to achieve that 100% mark potential.
That brings us to Section 3, the procedural framework. So how do we systematically tackle these complex examination questions without panicking?
By following this 5-step procedural framework, you ensure your algorithmic thinking is practically applied step by step. This is your ultimate success blueprint. Step 1. Deconstruct the question. Before you even think about writing a single line of code, break the question into logical steps. What are the command words? Step 2. Extract relevant data. Look at the scenario. What are the variables? What data types are explicitly mentioned or heavily implied? Step 3. Select the analytical framework. Are you using a single record structure here, or do you need an array of records to handle multiple entries? Make the choice and mentally justify it. Step 4. Execute with clear notation. This means highly efficient code implementation and clear, readable pseudocode. No sloppy indentation. Step 5. Present with correct terminology. If you mean field, say field. If you mean identifier, say identifier. Imagine our Rush student Sam applying this. Instead of instantly writing messy code, Sam pauses. Sam takes 60 seconds to deconstruct the command words. Sam extracts the data types. Suddenly, that flawed, rushed paragraph transforms into a structured, high-scoring response. Practical application in computer science isn't just about making a program run on a compiler, it's about designing algorithms and presenting them so clearly that an examiner knows exactly what your logical flow is.
Let's jump to Section 4, the method mark strategy. Now, what's really interesting here is how this specific strategy can literally save your exam score from disaster. Stop scrolling. Subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCS to excel in your Cambridge examinations. We've helped thousands of students improve by 2-3 grade boundaries. Join them right now by subscribing to at acetheexams_IGCS and turn on all notifications so you never miss our weekly exam strategy sessions. All right, back to the strategy. Method marks are awarded for the process, saving you even if the final answer is totally wrong. This is an official, massive examiner alert. Students lose a staggering amount of marks by not showing their working. Let's say you're writing a complex algorithm to update a record structure inside a loop, and right at the end, under the pressure of the clock, you make a silly arithmetic error, or you mess up your array index counter. If you just slap down the final answer without showing the steps, you get a 0, completely failed. But if you adopted the method mark strategy, if you rigorously showed your step-by-step decomposition, your data structure selection, and your systematic analysis, the examiner awards you crucial marks just for the process. This comparison perfectly illustrates why you must never, ever skip straight to the end. Let's do a quick interactive workshop mental exercise. Imagine a complex data table on a screen in front of you. You have exactly 60 seconds to extract the core trend. If you just guess the final trend and you're wrong, you get nothing. That's the showing only final answer approach. High risk, 0 reward. But the showing step-by-step decomposition approach provides a vital safety net. You are essentially leaving a breadcrumb trail of your logic for the examiner to follow. Even if you don't reach the final destination perfectly, the examiner can follow your breadcrumbs and say, ah, okay, I see it. They understood exactly how to declare the record, they knew how to access the field using dot notation, they just made a minor logic error at the very end. You still walk away with 70 or 80% of the total marks for that question. Your mark potential progress bar still shoots way up. So, step-by-step working is non-negotiable.
Let's move to Section 5, Top Examiner Warnings. We're going to dig deep into the principal examiner reports to see exactly where students consistently drop easy marks.
Here are the top 3 mistakes directly from the Cambridge examiners. Number 1. Students forget to check overflow and edge cases when dealing with record structures. If a record holds an integer for a gaming high score, what literally happens when that score exceeds the maximum allowed value? Does the program crash? Number 2, forgetting boundary conditions. This ties directly into rigorous testing. When you write an algorithm, you must test the boundaries, the absolute minimum, the absolute maximum, and just outside those boundaries. Number 3, answers are not specific to the context given in the question.
Remember our hypothetical student, Alex? Alex writes totally generic answers. Let's play Find the Flaw. If I give you a paragraph about a library database and you write, I will use data item A and data item B in my record, that's the flaw. The examiner will strike a red line right through that. Your answer cannot just talk about generic items. You must talk about book title, ISBN, and author name. You must anchor your theoretical knowledge in their specific reality to turn those red marks into green check marks.
To remember these potential pitfalls during the immense pressure of an exam, try using a visual story method to encode the rules in your memory. Panic can completely wipe your short-term memory in the exam hall, but our brains are naturally wired for stories and visual metaphors. Remember our street artist theme? Visualizing helps. Imagine a literal physical metal filing cabinet. That cabinet is your array of records. You pull out a single heavy manila folder. That is your specific record structure. Inside that folder, you have completely different types of paper. A glossy photograph representing an image data type, a typed letter representing a string, a crinkled calculator receipt representing an integer. Visualizing the structure like this makes it infinitely easier to remember how different data types sit under one single identifier, which is the name written on the folder tab. Try creating your own vivid visual stories for boundary conditions and edge cases. It makes the abstract, highly technical computer science concepts incredibly concrete.
Finally, let's explore Section 6, Critical Analysis and Evaluation. This is where you present your reasoning to secure those top-tier A-star marks.
When an exam asks you to compare approaches, say, using an array of record structures versus using multiple parallel arrays, you must use a rigorous structure. First, explicitly identify both similarities and differences. Don't just list the differences. Second, use comparative connectives, words like whereas, conversely, or similarly. This signals to the examiner that you are engaging in structured reasoning. Third, support every single comparison with evidence derived directly from the scenario. And finally, draw justified conclusions about the relative importance of your findings. You solve systematically, you check for reasonability, and then you make a highly justified recommendation. This ties into the final system for top marks: command word decoding, the Peel framework, and a time management matrix where you allocate specific minutes to planning, writing, and reviewing based on the marks available.
If you are asked to evaluate the quality of your algorithm, examiners are looking for you to thoroughly assess three specific components. First, time complexity. How fast does your algorithm actually run as the amount of data in your record structure grows exponentially? Second, space complexity. How much memory does your solution use? Record structures can be much more memory efficient and logically cohesive than poorly managed, sprawling parallel arrays, but you have to explain exactly why. And third, edge cases. What is the effect on performance when the algorithm encounters bizarre, completely unexpected data? A top-tier, grade-saving evaluation doesn't just confidently state, my algorithm works. It critically says, my algorithm works efficiently in time and space, and here's exactly how it handles an unexpected edge case without crashing. That's the level of depth we are aiming for.
So, the crucial takeaway here is to embrace structured reasoning. Are you ready to prioritize the process over just finding the right answer and secure those method marks by showing your work next time? Students who implement these exact computer science strategies see an average improvement of 2 grade boundaries, but that only happens if they practice consistently with our weekly explainers. Here's your final reminder. Subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCSE to excel in your Cambridge examinations. Subscribe right now to @acetheexams_IGCSE and click that bell. Don't let another exam pass you by. Also, drop a comment below with your exact target grade for computer science and the absolute biggest challenge you're currently facing. Our team responds to every single comment. Like and share this explainer with a study partner. Ace the Exams. Your Cambridge success starts here. See you next time.